Section 4.5 talks about the substitution method. Now, there are 5 techniques of integration. We're going to focus on one of them, and it's the substitution method. In this class, in the next semester, 5B, you're going to focus on the remaining 4. So for now, we're going to focus on one, and in one direction only. This has 2 directions. We're just going to focus on one of them. This is what it says. If you're integrating a composite function in which the derivative is being multiplied by that composition, then you're going to let u equal the inside of the power function, kind of what we did with the chain rule when we took derivatives, if you remember. You're going to let u equal the inside of a power function, the denominator of a fraction, the argument of a trig function, and so on and so forth. So it's almost identical to the chain rule. So when we say here, integrate the following, well, you're going to pick u. You're going to let u equal, and again, you're trying to eyeball the inside of a function. In this case, this is the inside of a power function. For starters, if I let u equal 2x squared plus 7, and if I take a derivative, du dx will be 4x, and if I cross multiply, this is the new trick, if I cross multiply, du will be 4x dx, and I notice that 4x dx is right there. So if I rewrite this integral with u being replaced by 2x squared plus 7 to the 10, and the blue will be simply du. And now when I glance at this, say, wait a minute, I know how to integrate this. This is a power function. So if I'm integrating a power function, I add 1 to the power, and I divide by that, plus c, and that's going to be I need to replace u back, and if you remember what u was 2x squared plus 7. If I take a derivative of this, I should get the integrand right there. So that's pretty much it. Now if you let u equal the wrong thing, well, it wouldn't work, and you'll know that wait a minute, I made a mistake. Few problems, and I'll show you how to start figuring out what u is a lot quicker. So if I look at this problem, I notice the power function is this. If I let u equal the sine of x, now du dx, derivative of sine is cosine of x, and if I cross multiply, du is the cosine of x dx. So this becomes the integral of the square root, and this is what I let u equal. And I notice that cosine of x dx I could replace by a du, and this is again a power function, that's u to the 1/2 du, add 1 to the power, divide by that. So if I divide by 3/2, that's the same as multiplying by the reciprocal, that's 2/3 the square root of u cubed plus c. You could leave it to the power of 3/2 if you wish, and what was u? U was the sine of x. And there it is. Now one more problem, and I'll tell you how this works. Again, how to check before you start. The inside of a power function is right there. I'm going to let u equal x to the 4th plus 1. So I let u equal the inside of a power function. Du dx is 4x cubed, and if I cross multiply, I'll get 4x cubed dx. So we're going to start skipping this step and jumping straight to this by writing dx at the end. Now when I make my substitution, well, there's my u to the 5th, and I notice x cubed dx is right there, but there's a 4 standing in the way. You could be off by a constant. That's not a problem. I could say x cubed dx is du divided by 4. And the 1/4 I could always drag up front, whether I'm taking a derivative or integrating. Now, this, the integral of u to the 5, add 1 to the 5 u to the 6 over 6 plus c. So I could say this is 1 over 24 times u to the 6 plus c, and u was x to the 4th plus 1. And there it is. Now, I'm looking at the next batch, and this is how I'm going to start doing this. I want to pick a u, but I should know that du should be whatever's left over. So I'm thinking, if I let u equal x to the 5th, is the derivative of x to the 5th x to the 4th off by a constant? Is okay. It is. Then I'll know that we're heading in the right direction. So I would let u equal x to the 5th. I know that du is 5x to the 4th dx. So this is the cosine of u. And x to the 4th dx is du divided by 5. The du and the 1/5 I could put up front. So that is 1/5. What do you take a derivative of to get a cosine? Derivative of sine is cosine. And all what I have to do is substitute what u was, and u was initially x to the 5th. And again, if I take a derivative of my answer, I should get the integrand. So I'm glancing at this, say, okay, well, let's say, if I let u equal this, is the derivative of that a sine? And if it is, then that's the way to go. If not, then choose something else. 3 plus the cosine of t. Well, the derivative, that's a 0. That's negative the sine of t dt. So I'm going to make my substitution. There is my u under a radical. And my du is really sine of t dt. Well, I could divide both sides or multiply both sides by a negative. And that will simply be a negative. And I could always take the constant up front. So that is negative the integral of u to the 1/2 du. Add 1 to the power. Divide by that. So that is negative 2/3. Again, you could write it as a radical. You could leave it as it is. It doesn't really matter. It's the same thing. And I need to replace u back. U was 3 plus the cosine of t. So this is called the substitution trick. Now here I have a couple of options. I could let u equal the inside of a power function. I could let u equal secant. Is the derivative tangent squared? It's not. So not the way to go. I could let u equal tangent. Is the derivative of tangent secant squared? It is. So that's the way to go. So if I let u equal, and here we are, I'm letting this be my u, so and it's being squared. And do you notice that secant squared dx is right there? So pretty soon you start looking at a problem and thinking, well, if I let u equal this piece, would du be the rest? And that's how you figure out how that works. So that's u cubed divided by 3 plus c. And I need to replace u back. And u initially was replaced by the tangent of x. So, not that bad of a section. Very efficient and the most used. Here, well, if I let u equal the angle, is the derivative of a square root 1 over a square root? Well, yeah, it is. If I let u equal the square root of x, du is 1 over twice the square root of x dx. So here I have too many radicals floating around. I should do this in order so I don't get mixed up. That's the cosine of u. And du dx over radical x, I can replace by 2 du. And what do you take a derivative of to get cosine? The sine of u. And I need to replace u back. And u initially was radical x, and there it is. So this is what you take a derivative of to get this, and you could check. If I take a derivative of twice the sine of radical x, that is twice derivative of sine is the cosine of radical x times the derivative of radical, which is 1 over twice radical x. The 2's cancel out, and I'm left with cosine of radical x over x. You could check any time. Taking a derivative is a lot quicker than integration. Integration takes a lot more work and more time. Again, here I'm thinking, what should I let u equal? There are too many things floating around. Well, the inside of a power function. Let me start with that. If I let u equal the sine of x, du is the cosine of x dx. So let me see how this works. This is replaced by my u. It seems cosine of x dx, oops, it didn't change colors for some reason. Cosine of x dx is right there. So that's going to be my du. All of that mess. And do you see that there's a cosine left? What do you take a derivative of to get cosine? Sine. And all what I have to do is replace u back and I'm set. And u in this case was sine of x. There it is. And if you take a derivative of that, you'll get that back. Oh boy. Okay, we just did that. I didn't change it. I'm sorry, my mistake. That's okay. Let's leave it there. The next set of problems. I was supposed to change that and I forgot all about it. So ashamed. How about this problem? Well, what should you let u equal? Well, think about it. When you take a derivative, you want that to be your du. What do you take a derivative of to get secant? Tangent. Or even better, so I don't have to do integration by substitution twice, I would let u equal not tangent, I'd let it be the whole thing, 1 plus tangent, because derivative of a constant is 0. That saves me 2 substitutions. Derivative of tangent is secant squared of x dx. So this becomes the integral of, and let's see how this plays. That is my square root of u, and all of that, oops, all of that mess is my du. So that is the integral of u to the negative 1/2 du. Add 1 to the power and divide by that. So that is twice the square root of u. And u initially, when we set it up there, was 1 plus tangent of x. If I look at this problem, well, it looks messy, but again, normally I let u equal the inside of a power function. Now what if that doesn't work? That's 5b. What's du? 3x squared plus 2x dx. And look at that, magic. Well, we're picking these problems to match. I meant for that to be a squared. My mistake. You're not there yet. So this becomes the integral of u squared du. That is the integral of u to the negative 2 du. Add 1 to the power, divide by that. So that becomes negative 1 over u, and u happens to be x cubed plus x squared plus 3. And if I look at this problem, so here I notice, well, if I let u equal 2x, the inside of a power function, that's not working. The root of that is 2 dx. That doesn't change anything. So what? Let u equal the inside of a power function. Let u equal sine of x. The root of sine is cosine. That's not working either. But if I think of this as sine of 2x is twice sine of x cosine of x. And if I let u equal the entire first piece, if I let u equal all of this, the derivative of that, bring the power down, subtract 1 from the power, times the derivative of the inside. Chain rule. dx. So I could say that's the integral. That's an ugly integral. There we go. So I let u equal all of this. And du is really all of this part. Without that trick, it's very hard to see. That's u squared over 2 plus c. That is, and what's u? U is the sine squared. So I'm going to take the sine squared of x and square it. That's a fine answer, of course. Or you could say that is the sine to the fourth of x over 2 plus c. Next problem, I have two options of doing this, and I'm going to do it both ways for both problems. So I'm going to copy that twice. So here, I could let u equal the inside of a power function. Du will be 3x squared dx. This will become the integral. This is my u squared. And I know the drill by now. X squared dx is du divided by 1/2, so I could put the 1/2 up front. That is 1/2, and if I integrate, that's u cubed divided by 3, and that is 1/6, and u is x cubed plus 4, evaluated from 0 to 1. So you could substitute the 1 in, and you'll get 1/6 into a 1 in, that will be 1 plus 4, that's 5, minus the 0 in 4, and that will give you 1/6 times 1, which is 1/6. That's one way of doing that problem. Another way you're not going to like in the beginning, but I strongly suggest that you start doing, it will save you a lot of steps, not in this class, in the next class. In this class, it will save you a step. The same process, let u equal x cubed plus 4, and du is still 3x squared dx, that didn't change. This becomes the integral. You put a u into the second power, and x squared dx is du with a 1/2. Change the limits on the integral. When you say this is the x, that's x equals 0, and there's that change at the u sub every time. Put a 0 in there. That's from u equal 4, and put a 1 right there. U equal 5. That will be 1/2, and I don't have to go back to x anymore. You could do that only if you have a definite integral. Definite integral means you have the limits on the integral. So that would be what? That would be add 1 to the power, divide by that, evaluated from 4 to 5. So that's going to be, okay, I see I made a mistake on the previous problem. My mistake. Actually, what I put there was fine, but it was supposed to be cubed. So when I put 1 in, 1 plus 4, that's 5 cubed. When I put 0 in, minus 4 cubed. Right? And on a test, you could leave it like that. That's not a problem. Or you could work it out. It's not that big of a deal. That's 125 minus 64, right? That's 1. 6 out of 12 is 6 over 6. There. Or you could leave it like that. But here, you'll notice this is 1/6. If you plug that in, that is 5 to the third minus 4 to the third. So it saves you a few steps. Actually, it saves you really 1 to 2 steps in this section, but a lot more in the next section. So here I'm going to do this problem again, both ways as well. I want to make sure you see it, and I'm giving you the option. In this class, it doesn't really matter much, but I strongly suggest. Oh, it didn't copy for some reason. There we go. Not copied. Very good. So, first step is for you to say, you know what? Let u equal the inside of a power function. We got it. Du is secant square root of x dx. There is my u. There is my du. And here you could say, you know what? I'm not going to worry about the limits on the integral until the end. That's the integral of u to the 1/2 du. That is the integral, add 1 to the power. So that is 3/2, divide by that 2/3, right? And then you're going to have to say that's 2/3, and u initially was tangent of x. There it is. And now I'm going to evaluate that from 0 to pi over 4. Throw the pi over 4 in, and you will get 2/3 times tangent of pi over 4, which is 1, to the 3/2, minus, put a 0 in, you get 0, so that's 2/3. No big deal. I strongly suggest that you use the alternative. I strongly suggest you let u equal tan of x. Du is secant. So this work is the same as this. Square root of u, du, the integral. Change the limits. If x equals 0, tan of 0 is 0. If x equal pi over 4, tan of pi over 4 is 1. I don't have to go back to x. This is u to the 1/2. Add 1 to the power. Divide by that. Evaluate it from 0 to 1. Throw the 1 in. 1 to the 3/2 is 1. 0. That's 2/3. So I'm going to give you the option to do whatever you want. I strongly suggest you do that. One thing to know about even odd functions, that will come up in the next section a bit more. If you're dealing with an even function is a function that's symmetric with respect to the y-axis. So that's an even function right there. If the right half and the left half are identical. If you're integrating, the key is negative b to positive b, so the same symmetrical area. If f happened to be an even function, then that would be 2 times this area, because those areas are the same. A lot of times 0 is easier to play with than, that should be a b. My mistake. There. And if you're dealing with an odd, and that's the more powerful statement, an odd function is symmetric with respect to the origin. So if you have a piece on the right, the left matches. So if I'm looking at this area, and this area happen to be exactly the same, again, the key is from negative b to positive b. Those will undo each other, and you'll end up having an integral being 0. Remember, I did mention it slightly when I was explaining that this means kind of like displacement. So if you move backwards from where you start and then move forward the same distance, it's like you didn't move at all. That's an integral. Area is a different story. That's the next section. So if I look at this problem, well, the u sub doesn't work on this. No matter what I try, it doesn't work. But do you notice that it's from negative pi over 4 to pi over 4? That's a key. F of x is x to the 10 tangent to the 5th of x. F of negative x is negative x to the 10 tangent of negative x to the 5th. F of negative x is x to the 10. Isn't that negative tan of x, because tangent is odd? And if you raise it to a 5th power, so if you remember, if f of negative x equal f of x, then f is even. And if f of negative x equal negative f of x, then f is odd. So this is an odd function. If you know it's odd and you're integrating from negative a number to the same number, that's automatically a 0. and you don't have to do any work except show that it is odd. And that's pretty much it for this section.